Alright, here we are in our last parallel RC circuit. This is going to be the only video we do that shows a multiple component in a branch. And you can see here branch 3 has two capacitors, C2 and C3. We're not going to spend a whole lot of time talking about total capacitance in series or total capacitance in parallel because we have covered them in previous videos. So we're just going to get started right off with the math. We're going to start with branch 2. So very familiar formula, capacitive reactance will give us the ohmic value of C1, which is in branch 2. And that is 13.54K ohms. Now we're going to do the same thing for both C2 and C3. We're going to use the same formula, I'm just going to put in the different numbers, and we get an ohmic value for C2 of 8.09K and C3 of 12.06K. Now, we know from previous videos that once you have capacitors in their ohmic value, once you have capacitive reactance, you can add them in series and reciprocate in parallel, just like all the other components. So C2 and C3 are in series with each other. So I can add the ohmic value of C2 and C3 together to get a total branch ohmic value of 20.15K. Once I have that, I can reciprocate to get a total capacitive reactance. So I'll use my reciprocal formula. I'll put in branch 2's ohmic value of 13.54K and branch 3's ohmic value of 20.15K, and I get a total ohmic value of 8.1K. Alright, then we take that and we put it into our impedance formula, which is the ohmic value for the total circuit. When we're familiar with that formula, we take our total resistance, which is 12K, and our total capacitive reactance, which is 8.1K, and we get a ohmic value for the circuit that is 6.7K ohms, which seems reasonable considering our rules of it must be smaller than the smallest value. Okay, once we have our total ohmic value, we can look for current. So we take our voltage divided by our ohmic value, and we get a current of 11.94 milliamps. We're going to look at branch currents next. So you should be pretty familiar with this process, especially for B1 and B2, as it's going to be just the same as the others that we've done. For branch 1, we take voltage divided by resistance, 80 divided by 12K, 6.67 milliamps. For branch 2, we take voltage divided by capacitive reactance, in this case 80 divided by 13.54K, and we get 5.91 milliamps. Now for branch 3, of course, we're going to use the total ohmic value of the branch, so we are going to take 80 divided by 20.15K, and that gives us a current of 3.97 milliamps. Now we do have to take it a step further there in branch 3. With branch 1 and branch 2 only having one component, R1 and C1 will be a voltage of 80 volts. However, on branch 3, C2 and C3 is where we will see the voltage split. So a portion of 80 volts will be on C2 and a portion will be on C3, and those two voltages added together should equal 80 volts. Alright, let's take a look at that. What we're going to do is we're going to take the ohmic value of C2, which is 8.09K, and multiply it by the branch current, which is 3.97 milli. We get a voltage of 32.12 volts. We're going to repeat the process with C3. We're going to take the ohmic value of it, which is 12.06K, and multiply it by the current of the branch, which is 3.97 milli. And we get 47.88 volts. When you add those together, you get 80 volts. So, way to double check that you did your math correctly and you do have the right voltages for those components. So that's really the big difference when you have multi-components in a branch. Remember, yes, your branch has 80 volts to it, but if you have multiple components, the voltage is going to be split up amongst the components. Now, if there were more, it would be split 3 or 4 ways instead of just 2 ways like this. But when you add those voltages together, they should equal that applied voltage. Alright, and then of course you can always use your current formula if impedance is intimidating for you. All you have to do is get your individual branch currents, add your like branch currents together. In this case, 5.91 added to 3.97 gives me a 9.88 milli. That combined with my resistive current of 6.67 milli into my formula, and I get something that is pretty close to total current, within hundredths of total current, which is 11.94 milliamps. Alright, and that is a parallel RC circuit with multiple components in a single branch. And next we'll probably be looking at LCR circuits.